It is my great pleasure to dedicate this talk to Victor Dodonov, who has done outstanding contributions to quantum physics in all aspects of quantum physics. The talk is about the Grothendieck bound in a single quantum system and ultra-quantum coherent states. What I mean by ultra-quantum, I mean near the Grothendieck bound, and half of my talk is to explain what a Grothendieck bound is. Let's assume that we have some d times d complex matrices, theta, that satisfy this absolute value here is less than 1, where AR and BS are scalars inside the unit disk. And then I call that classic C of theta for C for classical. And this is classical in the sense that this AR and BS are scalar quantities in the unit disk. Now, the Grothendieck theorem replaces the scalars in the unit disk with vectors in a d-dimensional Hilbert space, which are inside the unit ball. So I write this like this, Q for quantum. And here, because I take the bra and ket to have length 1, I put these parameters lambda and nu, which are less or equal to 1. So these vectors lambda u and mu v are inside the unit ball. And that is quantum in the sense that the scalars have been replaced by vectors. And what Grothendieck proved is that this quantity, that Q of theta, when that C of theta is less than 1, then that this quantum of theta is less or equal to what is now known as the complex Grothendieck constant, because there is another constant for real Hilbert spaces, but for quantum mechanics we're interested in complex Hilbert spaces. So what Grothendieck did, he proved that this Q of theta is always less or equal to this kg, the complex Grothendieck constant, and its exact value is not known in spite of a lot of effort, but it's known that this that approximately is around 1.4049. So the important thing is that when the classical quantity takes values less than 1, the corresponding quantum quantity takes values up to 1.4049, a bit less than that, because this constant, as I said, its exact value is not known. So that kg, the Grothendieck bound, is some kind of mathematical ceiling of the Hilbert space and of the quantum formalism, which is related to the Hilbert space formalism. Now, I'm particularly interested in what I call Grothendieck region, which is between 1 and kg, because this is classically forbidden that C takes values by definition less than 1, and therefore that this region between 1 and kg cannot be approached classically. It's forbidden classically, but it's quantum mechanics at the end, at the edge, near the upper bound, which is this Grothendieck bound. Now, Grothendieck's paper, the original paper, which actually was published in a Brazilian journal in 1953, used tensor products. And for this reason, all previous quantum work was for multipartite entangled systems by Cyrillson and many others. And they linked this with the Q greater than 1 when the quantum quantity takes values greater than 1 with violation of Bell-like inequalities. On the other hand, all later work, mathematical work, did not use any tensor products. They proved that it can be done without tensor products. And for this reason, I used it in the context of a single quantum system, so there is no tensor products on entanglements or anything like this. And the first part of my talk, what I do, I express that Q, which I showed here, that quantum quantity, as a trace of products of matrices, because quantum mechanics is most of the quantities are trace of some products of matrices. And they are arbitrary matrices, but they are normalized with a prefactor, and this is inappropriate to quantum mechanics. Now, it's not easy to find examples with Q that quantum quantity greater than 1. And indeed, I will mention that there are many physical quantities where you have some unitary operator U, and so you have some quantum state on the left and another quantum state, or the same quantum state on the right. And for these quantities, which are very, very common in quantum quantity, in quantum mechanics, you can prove that this gives Q less or equal to 1. So in order to go to Q greater than 1, it seems, at least from trial and error, that the examples are rare. And in this sense, examples with Q greater than 1 is some kind of new territory of quantum mechanics. And I will show that some examples who violate this, who enter that region Q greater than 1, are some kind of novel coherent states, which I should say from the outset have nothing to do with Heisenberg-Weyl group or SU2 or uncertainty relations or anything like this, or eigenstates of anything and so on. So I will explain why I call them coherent states when I come to it. Basically, there is a resolution of the identity in terms of them, and they are invariant under some group, which I will explain when I come to it. And I call them ultra quantum in the sense that this Q is greater than 1 and goes near this Grothendieck bound. Another thing which I will discuss very, very briefly is that they violate, and it's another totally nothing to do with Grothendieck now, they violate some Frechet probabilistic inequalities, which is some kind of analog of Bell-like inequalities for a single quantum system. And in this sense, which is a different angle from the Grothendieck angle, they are deep into a quantum region. I should say that much of the work, there is a lot of work in quantum mechanics in the so-called classical quantum transition, this semi-classical region. The talk that I give here is in the opposite region, in the ultra quantum. So it has nothing to do with the semi-classical. I try to go in the other edge, the ultra quantum. So let me express, first of all, that Grothendieck Q is a trace of products of matrices, because this is good for quantum mechanics. So first of all, some definitions. I introduce a set I call GD of complex matrices for which this C theta is less or equal to 1 for scalar quantities inside the unit disk. Now, if you have an arbitrary matrix theta, then you can calculate the supremum here, which is G of theta, and then if you normalize that theta over G of theta, you get immediately a matrix in that GD. So what I'm saying, if that is too large, divide it by the maximum value, and then you get another theta, which belongs to that set that I want. Another thing, if I have a D times D complex matrix M, then I define a normalization constant, which is the maximum of all the values in a row square, and then you take the square root, and you do this for all rows here, maximum over I, and you find this maximum value. And I call as D the set of matrices M which have an M less or equal to 1. Now, again, if you have an arbitrary matrix, you calculate this, you define that matrix, you normalize it like this, and then that matrix belongs into this set that I call here as D. And now, the Grothendieck theorem that I showed earlier, that Q quantity that I showed you at the very beginning here, you can write it as the trace of a matrix theta and matrix V, another matrix W, where theta belongs into that set GT that I defined here, and M belongs into that SD that I defined here. And this is less or equal to the Grothendieck constant. Now, if you have arbitrary matrices, you don't have that. You simply normalize them. You divide theta over that G of theta, V over that N of V defined here, and that W and you formulate the Grothendieck quantity, the Q, like this, and is less or equal to this Grothendieck constant. Now, a necessary but not sufficient condition in order to have Q greater than 1. As I said, GD is the set of complex matrices where this quantity is less than 1 when these scalars belong to the unit disk. Now I define another smaller subset, where this is less than 1 when the sum of this is less or equal to D, and the sum of this is less or equal to D. You see, if this is true, then this is true, but not the other way around. And for this reason, that GD prime is a subset of GD. And you can show, and that's my first result, that a necessary but not sufficient condition in order to have that Q greater than 1 is that this, for normal matrices, is this result, that this matrix theta belongs to the difference between these two sets. That's GD minus GD prime here, set minus. And now it is, as I said, that for an arbitrary matrix theta, that's G of theta, theta normalized with G theta belongs to that set. But it's a bit difficult to find that G theta exactly for an arbitrary matrix. But you can show an inequality where G of theta is less or equal to D times S maximum is the maximum singular value of theta. Now, I will deal mainly with normal matrices, and then that S maximum is the maximum absolute value of all eigenvalues. It's equal to this, or this is called the spectral radius. And then for lambda, if I have lambda less or equal to this, 1 over D E maximum, that lambda theta belongs to the smaller set, and therefore Q is greater than 1. If I can prove not less or equal, but if I can prove a strict inequality, that's G of theta to be less strict inequality than D maximum, then there is some window between 1 over D maximum and 1 over G theta, and then that lambda theta belongs to this difference of the two sets, and then maybe that Q is greater than 1. I say maybe because it's necessary but not sufficient condition. So I have here a necessary but not sufficient condition in order to try to find examples where this Q greater than 1. My first family of examples, and I will explain why I call them coherent states. I consider 6 states in H3, three-dimensional Hilbert space, and they're nothing related, as I said, with Heisenberg-Weyl group or SU2 or uncertainty in relations or anything like this. I consider these 3 families of vectors where that Z, the absolute value is equal to 1, that Z belongs in the unit circle. And then I can show easily that I have a resolution of the identity. So I have the first property of coherent states. And the resolution of the identity is like this. I can mention that the span of these 3 states and also of these 3 states is the whole Hilbert space, but you don't have resolution of the identity in terms of the 3 only or the other 3. Resolution of the identity is much stronger property than the fact that the span is that H3. So in order to get resolution of the identity, I need all 6, and the resolution of the identity is here. One property of these states is that I have a discrete isotropy. If I take any of these states here, AR, and I take the overlap with all the others, and I have a set of 6 numbers here, that set is the same for all R. It does not depend on R. And therefore, a consequence of that is that the following sum, if you create that sum here, for S equal 0 to 5, all of them, does not depend on R. And actually the value is exactly this. Another property of coherent states is that usually, if I have a set of coherent states, the whole set is invariant under the group of some transformations. That group, what it does, it maps one of the coherent states to another coherent state. It doesn't go outside from the coherent states. And that I have such a group here, which is that group here, that X is, I call it upward displacement matrix, and then that G3 is 1XX squared is isomorphic to Z3. And then the set of these 6 states that I showed earlier is invariant under these transformations in that group. But there is a difference with the standard coherent states, which is that the action of this G3 on these states is not transitive. I have 2 orbits, A0 goes A1, A2, and then A0, and A3 goes A4, A5, and then back to A3. Another difference with the standard coherent states is that some of the states here are orthogonal. For example, A0 is orthogonal to A3, but A0 is non-orthogonal to everything else. Also, A1 is orthogonal to A4, but A1 is non-orthogonal to everything else, and so on. Now, these orbits, I describe them with something that I call orbit matrices, but this is needed in some of the proofs, which I'm not going to give any proof here, so I won't go into this. Now, since I have 6 what I call coherent states in H3, I can define an analog of the Bergman representation where I represent a vector which in an orthonormal system it will have 3 numbers. This one, I can represent it with 6, which is this FR tilde, which are defined like this. Now, the Bergman representation is using an analytic representation. Here is a discrete structure. There is no analyticity, but I will just mention that there is work which extends the concept of analyticity into discrete structures, but I have not gone into this. But, I mean, for the uninitiated person, you might say, why should I represent a vector in a 3-dimensional space with 6 components? And the reason is because you have redundancy, and therefore, if I start with a state here and I calculate these 6 coefficients here, FR tilde, and then I add some noise here and I reconstruct the state F, it will be very close to the original one, much closer than if you do the same thing with an orthonormal basis. An orthonormal basis does not have any redundancy, and this is a bad thing in terms of noise anyway. If we didn't have redundancy in our speech, we wouldn't understand each other. A small error, spelling mistake would change completely the meaning, and we wouldn't understand anything. Redundancy is a good thing for a lot of things. Then I define the overlap of these 6 states, and I get a 6 times 6 matrix. And using the resolution of the identity, I prove that this is a projector. So this is this quantity. I can easily show it's a projector. And because of the discrete isotropy, I will come to a producing kernel in a second. You can show that the sum of this does not depend on R. This is the discrete isotropy in the context of this projector. You can write this projector as a block matrix with circulant matrices like this. And this is, again, needed in some of the proofs, but I'm not going to present any proof anyway. Because it's a projector, it has eigenvalues 1 with multiplicity 3 and 0 with multiplicity 3. And it acts, it's a 6 times 6 matrix. It acts on H6, which you can define it like this. You can write it like this, where the projector brings every state into that S3, and the other is the null state. So then a producing kernel formula is that if I have a vector in H6, I can write it like this, where that FR belongs to H3, and this belongs to H3 null. And then when the projector acts, acts on this, it leaves it as it was, but acts on this, it gives 0. Now, why I mentioned the reproducing kernel? Because one of the main applications of reproducing kernels is maximization problems. And I will show you in a minute that this Grothendieck Q corresponding to this projector gives greater than 1, value greater than 1. Now, the fact that it's reproducing kernel, I haven't gone into this. The reproducing kernels are used in maximization problems, and that might help to understand why I get a large value of Q, but I haven't gone into this. It's something that I'm thinking currently at the moment. Now, I just want to show you that the Q corresponding to this P gets values greater than 1. As I said at the time, that's G theta. You can show that it's less than D max, which for that projector, the eigenvalue, the maximum eigenvalue is 1, so I get 6. Now, I proved analytically that I have a strict inequality, that GP is less than 6, and actually I confirmed this numerically. Because it gave me the value of 5, so it is indeed less than 6. And then when that lambda is less than 1/6, that lambda P belongs to this G6 prime, and I have a window, because that GP is strict inequality less than 6, I have a window here, which it belongs, that lambda P belongs to that difference between the two sets that I showed it earlier. And then I take an example where theta is lambda P with lambda in that window, and then V and W that I showed you earlier is it gives this value, and I do the calculation, and I find that this Q is 6 lambda, which is greater than 1 when lambda belongs to that window. And then you can write this as a physical example if you want. You can write a density matrix 1/3 of P, and then this is an observable 6 lambda P, and then that Q you can write as a trace of this rho and this theta, so it's a physical example. Now we'll go to the fact that it violates very briefly the Frechet inequality, and let me explain what the Frechet inequality. What I'm trying to do is to show from a different angle, totally different, irrelevant to the Grothendieck work, that these are very quantum coherent states. If I start with a classical Kolmogorov probability theory where omega is a set of alternatives, and I have subsets where the intersection is the empty set, then the Frechet inequality, which is not difficult to prove actually, with a bit of set theory, is that the sum of n probabilities is less or equal to n minus 1. And this proof is based on the Bool's inequality. Now, Abramsky and Hardy used a similar kind of proof, but with Hilbert subspaces, and they call them logical Bell inequalities. And in many examples, they found the usual Bell inequalities. And I used this in the past again for multiple tight entangled system. But here in this context, I thought, why not to use them for a single quantum system? And so that HI here now are not tensor product. So in that context, what it says is that if I have subspaces of HD with this is intersection or conjunction of these subspaces equal to 0, then you calculate some probabilities like this, which is the trace of some density matrix, any density matrix you like, times the projector to these subspaces, and you can prove that the sum of n probabilities is less or equal to n minus 1, which is, the proof is very analogous to this. And then you can show many various quantum states which violate this, and they are also violated by some projectors related to these coherent states that I show, but I won't show details on this. I just want to say that it's an indication of their quantumness from a different angle irrelevant to the Grothendieck work. Another second family of coherent states is if I take now 12 coherent states in H4, and I have this, the columns of this normalized with square root of 3, that omega is, here is exponential of I 2 pi over 3, and that z is any constant in the unit circle, absolute value of z equal to 1. And then again, I have a resolution of the identity which is like this. I have a discrete isotropy property like I had before. If I take all these overlaps, do not depend on this R, and you find that the sum of this does not depend on this R. It's the same for all R, and it takes this value. Here, the set of these coherent states are invariant under transformation in that group. G4 is a bit bigger. It's isomorphic to Z4 again. That X is analogous to the other, but in a bigger dimension. And here you have, again, the action of the G4 is not transitive. You have 3 orbits here, A0 up to A3, and then A0, A4 up to A7, and then A4, and A8 up to 11, and then A8. And here you have, I define again this projector. I won't give it explicitly, it's a 12 times 12 matrix. And because of the resolution of the identity, is a projector which has eigenvalues 1 with multiplicity 4 and 0 with multiplicity 8. And then again, if you do the G corresponding to this projector, you prove a strict inequality is less than 12. So there is a window of values between 1 over 12 and 1 over GP. And in here, I get that this Q is greater than 1. And the final example that I will show, and I won't go into the details, is again in H4, I have 8 coherent states, which are these. And here again, that Z, absolute value of Z is equal to 1. The coherent states are the columns of this normalized with 1 over square root of 2. And then you can show this is the resolution of the identity, and you get all properties analogous to this, discrete isotropy, invariance under the group Z4 there, G4, which is isomorphic to Z4, and so on. I won't go into this. I will just conclude. What I did is, the first part was to formulate the Grothendieck theorem in a single quantum system. Previous work used it in multipartite quantum systems, and the reason for that is that Grothendieck himself originally presented the work in the context of tensor products. However, all later mathematical work emphasized that it can be done. It doesn't need tensor product at all. It's always in mathematics. The first paper uses 10 assumptions, and then they find that the 5 of these 10 assumptions are not needed. This is the case here. The tensor product is not needed at all for the Grothendieck theorem. Then I expressed that Q as a trace of products of 3 matrices which are arbitrary, and they are normalized with these coefficients. Then I showed that many physical quantities gave Q less than 1, especially basically it was what I showed at the beginning, that this quantity, which is very important, any unitary operator with some state on one side and another, or the same state in the other side, gives Q less than 1. So a lot of physical quantities are already excluded as a candidates for Q greater than 1. I was interested in an example where the Grothendieck is, where that Q is greater than 1, and I call this Grothendieck region, and introduced these coherent states which they had this resolution of the identity. They have the property of discrete isotropy that I showed. It was the set of these coherent states, it was an invariant under transformations in that group Gn, But perhaps the difference from standard coherent states is that I had some orbits here. The action of this group was not transitive, and that led me to some orbits in all examples that I showed. Then I introduced an n-tuple representation where it was the analog of the Bergman representation, but I did not have any analyticity here. And then I took the overlaps of these coherent states, and that gave me a projector. I proved that I can easily prove that it's a projector because of the resolution of the identity. And this projector led me to Q greater than 1, which is very near the ceiling of the Hilbert space formalism or of the quantum formalism. Now, the challenge is to generalize this to any dimension. And how can I find examples where Q greater than 1? There is where the reproducing kernel in further work might help me because, as I said, the reproducing kernel is used in maximization problems. I will finish in the way that I started. I dedicate this talk to Victor Dodonov for his outstanding contribution that he has done in all aspects of quantum physics. Thank you very much indeed.